What's up, guys? It's your best friend Hugh,
And Will.
and today we will be covering an exciting, amazing, and confusing topic called quantum teleportation.
Oftentimes, when people hear the word teleportation, they think of one thing being instantly blinked between two places. But we are here today to tell you how it really works, and hopefully you will walk away excited and interested about quantum teleportation.
The first mention of teleportation was in 1877 in an article called The Man Without a Body. Later, it was popularized in the 1960s in a show called Star Trek. This type of teleportation involves the transfer of matter, a physical thing, from one place to another at a seemingly infinite speed. However, this is not really what quantum teleportation is. Quantum teleportation was first mentioned in 1993 in an article called Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen Channels. This initial scientific article was merely theoretical, but it was not long until it became a reality. In 1997, a group in Italy managed to achieve the first experiment of quantum teleportation. First, though, we must explain what we mean when we say the word teleportation.
Unlike the physical teleportation of stuff, like in Star Trek or Harry Potter, quantum teleportation does not involve physical matter. Rather, it is the exchange of information, albeit quantum information, between two places. It is able to send this information because the two particles, oftentimes photons, have a certain quantum property called entanglement. And, to further explain the teleportation, we must go deeper down the rabbit hole to investigate what entanglement is.
We all know what the word to entangle means. It's the act of intertwining something together. In quantum entanglement, it is not too different. It's when you have a group of particles, we'll use two in our examples, that are connected together such that their actions are no longer independent. That is, if one particle does something, the other will do the identical thing. One moves up, the other moves up. One spins, the other one spins. This idea of entanglement is not as new as quantum teleportation. Back in 1935, a paper by Podolsky, Rosen, and Einstein looked into what Einstein referred to as spooky action at a distance. He coined the term because with the understanding of quantum mechanics at the time, such behavior was impossible. This is because the particles are separated by a great distance, and yet they know something about each other. As well, he thought that it was impossible to make information travel faster than the speed of light, which in entanglement it does. In fact, a team of Chinese scientists measured two particles 15.3 kilometers apart and found that the transfer of states between them happened at a speed at least 10,000 times the speed of light, which is about 3 trillion meters per second, or half the average speed of Gavin Cherry's 1600 meter split time. This was found to be the lower speed limit as well, meaning that with more precise instruments, we'd expect the entanglement speed to become even larger. You may be wondering now, where do you get yourself a pair of entangled particles? Are they for sale online, or do you just hunt around your house for them? As you might have guessed, this is neither the case. Rather, they can be produced through a process called parametric down conversion. In parametric down conversion, a photon from a strong pump laser is converted into two daughter photons by firing the photon through a certain type of crystal. These two daughter protons then have half the energy, but are entangled together.
Now that we understand quantum entanglement, we can understand quantum teleportation. As we said earlier, teleportation in the quantum sense involves the near instantaneous teleportation of quantum information between two entangled particles. Because of their entanglement, when the state of one particle is changed, the other must change along with it. This means that if a piece of quantum information is given to one particle, causing a change in its state, the other must receive that information in order to change its state too. This can be furthered by introducing a third unentangled particle to the system. If the third particle interacts with one of the entangled ones, the other entangled particle must also experience an interaction, essentially teleporting the third particle, though just its information, not the particle itself. The problem with this is that the near instantaneous teleportation can only be done with quantum information, and at the moment, that information cannot be interpreted without converting it first into classical information, think computer bytes, which can only occur at light speed.
Quantum teleportation is still a new discovery, so there are many ongoing studies into how it works. It has not yet replaced any practical applications, but scientists have been able to reliably induce quantum teleportation using photons. Currently, quantum experts are experimenting with teleporting electrons, but it is unreliable. If steps keep being made, it will not be long before electron teleportation is viable. As well, even so entanglement information travels 10,000 times faster than the speed of light, the experiments must send along classical information to convert the quantum data back into useful information, limiting the speed back to the speed of light. However, if quantum computers continue to develop alongside teleportation, hopefully we will reach a point where it is unnecessary to convert the classical information in order to be useful.
Quantum teleportation will become the foundation of all online activity. First, because it is extremely fast, and therefore information would be instantaneous across any earthly distance. Secondly, and more important to some, it is 100% perfectly secure. This is because by simply observing a quantum object, it changes its properties. This is a property called superposition. Think of Schrodinger's cat. The cat is in the box with the poison that will kill the cat at any unknown time. To an observer, they do not know whether the cat is alive or dead, and so it is both to them. By opening the box and seeing the cat's state, it instantly changes the state the cat is in to the observer, knowing that it was messed with. In this example, the cat is the particle, and opening the box is the act of measurement. When the particle is measured, its state is changed, so the receiver will know that it was measured. Therefore, because of the properties of superposition, any information you send would be spy-proof. Quantum teleportation with photons is not extremely practical. However, quantum teleportation with electrons can replace any digital classical information system we currently use, because all electronic devices involve the movement of electrons in order to operate. All computers, phones, toasters, TVs, or cameras could utilize quantum teleportation to instantly communicate across large distances, allowing for interactions without the impediment of lag or time delay between sender and receiver.
Now, for a quick summary of what we learned. Quantum teleportation involves the near-instantaneous transfer of quantum information between two particles. These particles must be entangled, a process where despite any distance between the particles, they have identical actions. Quantum teleportation is so amazing because it's incredibly fast and perfectly secure.
It currently is not practical, but with enough investment and research, it will be the future of all electronics. Quantum teleportation is a breakthrough field into the possibilities of the future. It is a great time for people to get interested and involved in the field. The only downside to quantum teleportation is I can no longer blame lag in my games.